Hey there everyone. In this video we will learn about the exponential functions and the logarithmic functions. Okay, so let us look at a pattern now. Okay, so this straight line is the graph of x is equal to y. Okay, you already know this, x is equal to y. Now what happens when we increase the exponent? This is x to the power 1 is equal to y. Now what happens when we do x square is equal to y? We get a graph like this, है ना? Alright, so the second line is your graph of x square is equal to y. Now if we further increase the exponent, suppose x to the power 10 is equal to y. So again you will find a graph that is leaning towards the y-axis. Now x to the power 10 will go like this. Okay, this is x to the power 10 is equal to y. And similarly, if you go on increasing the exponent, you will see a graph that is more inclined towards the y-axis. This means the greater the exponent, the greater is the growth of the graph. Growth means what? See, you look at the x is equal to y graph. For a small change in x, there will be equal change in y, है ना? And when you increase your exponent x square, अब आपने x की पावर 2 कर दी, तो ग्रोथ बढ़ गई आपकी ग्राफ की, मतलब आपकी छोटी सी आपने x की कोई भी कंसिडरेट वैल्यू इंक्रीज की, उसके अकॉर्डिंग y की वैल्यू कुछ ज़्यादा इंक्रीज हो गई एज कम्पेयर टू x इज इक्वल टू y. एंड सिमिलरली for x to the power 10 is equal to y, for a small change in x your y changes rapidly, so this is called growth. Okay, so you can easily see this, that as you go on increasing the exponent, the growth of the function increases. The higher the exponent, the higher is the growth of the function. Okay, so these are all your polynomial functions. You already know this. Okay. Now the question arises, we will go on increasing the exponent and will obtain graphs that are more inclining towards the y-axis, means the growth of the graph will go on increasing. But is there any other kind of function that has even more growth than the polynomial function? Now to feed that, you have the exponential functions. You see the exponential function. This is a polynomial function, x raised to any power is equal to y. This is polynomial function. Now if we have y is equal to b raised to the power x, any base b raised to the power x, these kinds of functions are your exponential functions. Okay, so you will see that exponential functions are even more increasing, even more larger in growth as compared to any polynomial function. This is your exponent 100, x raised to the power 100. Even if you take x raised to the power 1000 times, even then this graph will have better growth, more growth than the polynomial function. Now this is where the concept of exponential functions come into play. We will see how. Now this is your function, y is equal to b to the power x. Okay, so the graph goes like this. Exponential graph always goes like this for any base b. This is your real line, minus infinity to plus infinity. Alright, and the graph goes like this. Now the constraint is that your b should be greater than 1 always, because you see, if your b is 1, then y is equal to 1 to the power x. 1 raised to any power gives you 1 only. So in that case you will get a straight line, y is equal to 1. That means this line 0 1, this will be your graph. So the constraint for exponential function is that your b should be, b means the base to which your exponent is raised, b should be greater than 1. Now you will see one thing, that 0 1 is a point that you will get at any exponential function. You take any base, let b be the base be 5 to the power x. Here also if you put x as 0, 5 to the power 0, you will get 1, y will be 1 only. 0 1 will be the point. Means irrespective of what your base is, on what base you are going to draw your graph, this point is always going to come in the graph, 0 1. Okay, so this is your exponential function. Now you know a very familiar exponential function, which is your y is equal to e to the power x, where e is what? Something 2.71, right? So this is something you are very familiar with. This is a kind of exponential function. Okay, so there are a few properties of a exponential function. First of all, we will discuss the domain. Domain means all the values of x for which the graph exists. Okay, so you see this graph is valid on all the values of x throughout the number line. There is no point, no breakage where you will not get any value. Means the graph is continuous throughout the number line. Okay, so the domain of your exponential function is whole real line, minus infinity to infinity. At any point of x you will get some point y. Alright, now range. Range means all the y's where the graph gives a value, है ना? So you see, at any y less than 0, there is no value. The graph is not going beyond the positive y, है ना? So first of all, r minus means all the negative real numbers will not come in the range. We will only talk about the positive real numbers. And then one point is 0. Is 0 included or not? You see, this graph is an asymptotic graph. This graph cuts the x-axis at infinity, means it is leaning towards x-axis and coming nearer and nearer to the x-axis, but we don't know where this graph is going to cut the x-axis. So it is assumed that the graph cuts the x-axis, intersects the x-axis at infinity, extreme end. So at infinity you will get, at minus infinity you get the value 0. So 0 will not be included. So the range of this graph is positive real number. All the positive real numbers, anything greater than 0, even the minute, even the smallest value near 0 will come in the range, but 0 won't come in the range. Alright, so domain, range. Now third point is that your 0 1 will always be in the graph. 0 and 1 point will always be present in the graph. Alright, and you know how 0 1 is going to be present, because your function is y is equal to b to the power x. Alright, for if you put x as 0, y will always be 1 irrespective of the base. So 0 1 will always be present on the graph. Now comes the value of this function at the extreme ends, means at plus infinity and at minus infinity. Now you see, at plus infinity you go on increasing your x, and you see that your graph is also continuously increasing as you increase your x. So as you reach towards the infinity, this graph also reaches towards infinity, है ना? So at b to the power infinity, means if you put x as infinity, you get infinity only. Means as your x to which your base is raised, as you go on increasing the x, your graph also increases, है ना? So as you reach the infinity, your graph also reaches infinity. So b to the power infinity is infinity, and here the minus of infinity, the left extreme end. As you go on decreasing your x, the graph also tends towards this x line, x axis, है ना? As you go on increasing the x, the graph is also leaning towards x, and the moment you reach minus infinity, your graph intersects the x-axis. So at minus infinity, this graph will intersect, that means you will get the value 0. For any exponential function raised to the power infinity is infinity, and raised to the power minus infinity is 0. Alright. So you know, this fourth point will be this, you can write it in your own language. For very large negative value of x, the function is very close to 0. Means as you go on increasing the x to very large negative value, your function is very close to 0. Means we assume that our graph is going to intersect the x-axis at infinity, but we actually don't know where it is going to meet. That's why we assume that it is going to meet at infinity. Means for the very large negative value of x, the function is very close to 0. And similarly, for a very large positive value of x, the function is very close to infinity. That case, when the value is positive, on the positive x, the very large value of x will give a very large value of y. Means at infinity, your function will tend towards infinity. So these are some properties of exponential function. We had y is equal to b to the power x, where b is always greater than 1. Now this exponential function can be represented in the log form as log of y to the base b is equal to x. This is how the exponential function is represented in the log format. See, with an example we will try to understand this. You know, 2 to the power 3 is 8, right? Means 2 to the power x is something, is some y. Okay, so 2 to the power 3 is your 8, 2 to the power 4 is your 16, and so on, right? The base here is 2. Base is 2, exponent is going on increasing from 3 to 4, and so is the value going on increasing, right? So base 2 raised to the power 3 gives you 8. Now if we have to write this in log form, we'll write log of 8 is 3 and the base is 2. This is how you write it in log format. Now suppose your y is equal to e to the power x. Alright, so you will write log y is equal to x. The base of log will be e. This is how you represent exponential function in the terms of log. Similarly, 10 raised to the power 3 is 1000. Okay, so that means log of 1000 to the base 10 is your 3. Alright, now one thing, e is called the natural base. These are the terminologies, natural base, and 10 is called the common base. Alright, now let us try to make the graph of log function. We have an exponential function as x is equal to b to the power y. Alright, so that means log of x to the base b is equal to y. Alright, means y is equal to log of x to the base b, the same thing. Alright, so you see the graph of log function. Now here your point 10 is going to play a vital role. How? See, if you put x as 1, if x is 1, then y ultimately has to be 0, because anything raised to the power 0 is 1, right? And b cannot be 1. This is our constant, so y has to be 0. This is a fact. So in the log function, the graph of log function, point 10 is going to play an important role. So we'll fix this point first of all. 10, and for a fact you know that all the graphs of different log functions, means log functions with different bases, are going to pass through 10, because 10 will universally be here. Alright, irrespective of whatever your base is, if you put x as 1, then y has to be 0, right? So we'll fix this point. and the graph of log goes like this. This is the point 1 0. All right. This is how your y is equal to log x graph looks like. 1 0. Now you see log of 1. If you have to check log of 1, if you put x as 1, you will get 0, y as 0. So log of 1 is 0. You already know this. Log of 1 is equal to 0. That's why you see this point is going to play an important role. Now as you go on increasing the base from e to 9, the base is 9, if the base is 9, if the base is 10, your growth you see will go on decreasing like this. As you go on, suppose this is log x to the base 10. Now as you go on increasing the base, your growth decreases, and as you go on decreasing the base, suppose this is log 2, log x to the base 2. Now as you go on decreasing the base, your growth increases. So this is generally how log function works. All you have to remember is this, that point 1 0 is a pivotal point. All the log graphs will pass through this point. Why? Because as you put x as 1, y has to be 0. So 1 0 is an important point. All the graphs of log functions, irrespective of whatever the base is, the function, the graph will cross through 1 0 point. Alright, and one more thing is that as you go on decreasing the base from e, if it goes, e is 2.7 something, right? So if you go on increasing the base, okay, so if you go on increasing the base, the graph will tilt toward the x-axis, and if you go on decreasing the base, the graph will tilt toward the y-axis. So this is all about log functions. Now we will look at some properties of log functions. Now first of all, we will talk about the domain. Domain means the x, we will look at the x where the graph exists. Now you see, there is no point, there is no significance of the minus x's, the negative x, all the x less than 0. You see graph is not even crossing the y-axis, not coming in the left hand side part. Graph is fixed to the right hand side of the x-axis. So you already know for a fact that the domain is going to be r plus all the real positive real numbers. Why r plus? Because 0 will not be included, because we don't know where this graph is going to cut the x-axis. We assume that it cuts at infinity. Alright, so 0 will not be included. Domain is r plus. Range means we have to look at the graph and see where it is ranging from. So you see, from plus infinity to minus infinity, throughout the real number line, throughout the y-axis, you will get some point on the graph. Alright, so the range is whole real number line. Here, point 1 0 is pivotal point. Alright, and your graph function is always ever increasing. You go on increasing the value of x, the graph goes on increasing. So the graph of log function means the log function is an ever increasing function. Okay. Now there is a very interesting relation between y is equal to e to the power x and log of y is equal to x to the base e. Now there is an interesting relation between both these equations. One is an exponential function and another one is a log function. Alright, so you see, this is our line, x is equal to y. Alright, now log graph goes like this. This point is 1 0. The exponential graph goes like this. This point is 0 1. Alright, this is your y is equal to e to the power x. This is your y is equal to log x. you look at this graph carefully, you will find that the line x is equal to y acts as a mirror between both the graphs. Means both of the graphs are the mirror image of each other, and x is equal to y acting as the mirror between them. If x is your 0, then y has to be 1. If x is equal to 0, then y has to be 1 irrespective of whatever the base is. So this 0, 1 is going to come in every graph of exponential function, and here in log function, okay, y is equal to log x, that means e to the power x is equal to, no, e to the power y is equal to x. Alright, so if you put x as 1, so y has to be 0 irrespective of whatever the base is. So in log function, your 1, 0 plays a important role. In exponential function, 0, 1 plays an important role. Both of the graphs are mirror image of each other, where x is equal to y acts as the mirror line. Number 1, log of a to the base a is always 1. Always. How? Any base. You can take any. A can be any number greater than 1. For this, log a to the base a is always 1. How? Because if you convert it into exponential form, this will be a to the power 1 is equal to a. This is true for any a. Alright. So log a to the base a is always 1. The second property, if you have log p to the base a and you have to convert it into log p of base b. Okay, so if you have to change the base, in that case you will have log p to the base a is equal to log p to the base b upon log b to the base a. Alright, so this you can verify it on your own. Third and general property that you already know, if it is log p to the power n. Alright, in this case you already know it is equal to n log p. Alright, fourth property, this is also a general property, log ab, log a into b is equal to log a plus log b. And fifth property, log a upon b is equal to log a minus log b. So these three properties, I think you are familiar with these three properties. I think you are familiar with this also. Just see how you have to change the base. If you have to change the base of log, just do log b upon p divided by log b to the base a. Alright. Now comes the differentiation of exponential function and logarithmic function. So y is equal to e to the power x. So if you have to differentiate this, the differentiation remains the same. dy by dx will also be e to the power x. You know this. But you see, if e is raised to some function of x, right now it is e raised to the power x only. But if e is raised to some function of x, maybe suppose it is y is equal to e to the power minus x. Alright, so in that case you have to apply the chain rule. First of all, dy by dx will be, you know, differentiation of e raised to the power something is e raised to the power that only. So first of all you will have e raised to the power minus x, but further you will differentiate minus x also. So that will give you, so this gives you minus 1, right? So it is minus e to the power minus x. And similarly, if you have y is equal to e raised to the power cos x, now you see, e is raised to some function of x. The function is cos x. So in this case also, dy by dx is, first of all you will use this property only. So it is going to be e to raised to the power cos x. But further, cos x is also differentiable with in terms of x. So you will do d of dx. So this gives you cos x sin x e to the power x, e to the power cos x. So this will be your final answer. Now this is an implicit equation. dy by dx is given as 1 upon x. Alright, so this is the differentiation of log x. But you see, suppose y is equal to log of cos x. Alright, so now if you have to differentiate this, first of all, the differentiation of log function is 1 by x. Alright, so x here is cos x. So first of all it is going to be cos x only, but further cos x is also differentiable in the terms of x. So cos x is minus sin. So this gives you minus sin x upon cos x. So this is going to be your answer. Similarly, if it is y is equal to log x cube plus 2x square, suppose. Alright, and you have to differentiate this. dy by dx, first of all you will treat it as some function of log, suppose log n, and you have to differentiate this with respect to n. So what it is going to give you? 1 upon n only. So this way you will write 1 upon x cube plus 2x square. But further you know that this function, this term is also differentiable with respect to x. So you will further differentiate this and you will get 3x square plus 4x. So your total answer, complete answer will be 3x square plus 4x whole upon x cube plus 2x square. So these are the differentiation of exponential function and log function. Now let us discuss some questions from exercise 5.5 of NCERT. Okay, look at this question. Y is equal to e to the power sine inverse x. Alright, and you have to differentiate this. You have to find the differentiation with respect to x. So dy by dx, since it is a function, it is an exponential function, e raised to the power something. So first hand derivation will be e raised to the power sine inverse x. But then you have to see whether the exponent is further differentiable with respect to x or not. So in this case it is. So you will do d by dx of sine inverse x also. So this gives you e raised to the power sine inverse x on 1 upon under root 1 minus x square. Straight formula of differentiation of sine inverse x. So you get e raised to the power sine under root 1 minus x square. So this is your answer. Now look at this, log of cos x square e to the power x. Alright, y is equal to log of cos of e to the power x. Triple chain here. See, dy by dx is, first of all it's a log function, so the differentiation of log function is 1 upon the term, so it's cos of e to the power x, right? But this term is further differentiable with respect to x, so minus sine e to the power x. Alright, now e to the power x is further differentiable, that means you will differentiate e to the power x also, d by dx of e to the power x. Alright, so overall it gives you minus sine e to the power x upon cos e to the power x. Alright, and d by dx of ex is also ex. So this is your complete answer. Alright, you can further write it as tan e to the power x minus e to the power x into tan e to the power x. Alright, log of x, dual log function here. So if you have to differentiate this, differentiate the first log function. So this will give you 1 upon all that is inside log of x. Alright, but log of x is further differentiable, so you will differentiate this log x also. Log x ka differentiation 1 by x. So overall answer is x log x. Okay, I hope this is sufficient for you. Now again I'll urge everybody to solve as many questions as you can without looking for the answers from anywhere. And in case of any doubt, any query, you can simply reach out to me. Thank you.